Cool. So today we want to talk about memory safety, and also talk a little bit about other stuff if we have time. So last time, we just also get rid of this. Okay. So yeah, last time we talked about T's, right? Goals, the details, the challenges. So now we want to go a little bit deeper into the hardware. So we are gradually, moving from system to the hardware. And what we want to do now is looking more at the memory safety and security. Just let me give me a second. So I also set up the camera. Camera as well. So yeah, as I said last time, we talk about keys, and today we want to talk about memory corruption and memory safety. All right. Before that, I mean, a couple of logistic questions. So I mean, thanks everybody for putting your feedbacks on the quiz. Still haven't gone through the quiz, so I'll try to grade them soon. Part of the quiz, I mean, the goal of the quiz, as I said before, was mainly open-ended design questions, as well as helping you to think about some of these problems more deeply. I always think that quiz is also part of the learning process. So usually two things happens when you're doing a quiz. One is you have to go back and read some of the materials. That's one helpful part of it. And the second is that during answering questions, you kind of gather things around and think about it. So I mean, so that was the main intention. And as I said, we won't have midterms and finals. So just basically this and the next quiz that we're gonna have probably either in week 8 or week 9 would be the only two main things that we're gonna have before exams. For those of you who don't want to do the project, we're gonna have the third quiz at the week 10 to substitute that for your project. So those of you who don't want to do the project. Any questions on Zoom or in class? Okay. So let's get started and talk about memory corruption. So we want to talk about, what are the potential attacks? What is the vulnerabilities that we need to be worried about? The impact on the real system. What exactly can the attacker achieve? What would be the threat model? And then we're going to also talk about some mitigations and some defenses. All right. So these are the main three things that we're going to discuss today. And I mean, if you go back to the memory safety and memory corruption, is one of the very oldest problems in security. It's one of the main problems in security as well. And the problem is really this cycle of attack, defense, mitigation, and other new attacks, the defense, and this goes on and on and on for 30 years so far. So it's really what happens is one clever attack strategy comes out, then people start jumping on thinking about okay, how to fix it. That being fixed, either just usually introduce a new set of vulnerabilities, or there's another part of the problem, the part of the memory or part of the system is actually what create these attacks. And usually in all these scenarios, there's always this trade-off that you already know well between performance and metrics and security, right? So of course we can completely eliminate these issues, but that comes at very high cost of the overhead or the cost of the design and so on. So we cannot really completely get rid of that, right? So we always have to live with this trade-off, all right? And then the main reason especially for memory problems and memory bugs is usually these bugs coming from different complex software that we have in the system. It's really difficult for a very complex software system to find all the bugs. It's still an ongoing research problem in software security and in software engineering in general. And as I said, there is this evolving issue of attack. So it's not just attack itself is not something static. It's something that's evolving over time. And as I said, Defenses has to be also efficient. So it's not just, we want to remove this attack surface. We also need to be careful of all the other metrics. So the first thing that we're going to discuss is buffer overflow. Most of you probably have heard it, but we're going to actually go and talk about it because this is like one of the major issues in memory safety. Just by show of hands, how many of you already know what buffer overflow is? Okay. So, all right. So let's talk about what buffer overflow is. For that, we need a little bit of background. Somebody raise hands. You were just participating in the poll. Okay. So let me give you a little bit of background of like what buffer overflow is. And for that, we need to a little bit know how the memory layout and how the memory translation and address translation repeater works, right? So generally, the memory layout looks something like this, where we have different sections for each process that we have. We have data section, we have text section, and so on and so forth. The biggest part and the most important part is usually this part, which consists of heap and stack. Usually heap grows in this direction and stack grows in this direction. So it's not something they're not static as the data section or the text section or the environmental variable, but they actually can shrink or grow in size depending on the need of the system. All right. To understand this a little better, let's actually have a quick detour of memory management in modern processor. The first thing to think about is that, okay, we have something like a main memory in our computer and we have different programs, right? The question is that how we store these different programs and how do we run this different program, right? And as I said before, the main security requirements is the isolation. So we want to make sure that program A does not have access to program B and vice versa. And then for all these programs that we have in our system, that should be the idea, right? So none of them actually have to have access to their to each other's data and cannot be overwriting or reading some information from the others unless we explicitly ask them to do it. So for example, there are part of the memory that can be shared, but what we are mainly care about is having complete isolation between part of different programs, right? So how do we do it? So as I said, each program typically have different regions, and there could be that some part of the region is also shared among multiple programs. So in addition to have well-defined regions for each of these programs, part of it can be shared. And usually what happens is that part of the memory is also reserved for the operating system or for the system software itself. So if you look at the main memory will look like something like this. There will be some free spaces. There will be parts for different programs. There will be some parts that are shared between, let's say, program 1 and 2. And then there are parts that are reserved for the hardware or for the operating system. Mainly, for example, for storing the operating system itself, because the operating system itself is a program for itself, right? So we need to store that somewhere in the memory as well, right? So we usually reserve some part of the memory for that. And the memory management is basically just this set of rules and set of mechanisms in order to make sure that we have the isolation that we want, but also at the same time, we have the performance that we want, right? So if we have a simple machine that runs only one program, then we just give the whole program to the whole memory to that one program. But modern systems, as you know, many different programs run at the same time. So we really need to manage the resources available to each of these. So we kind of need to have a very intelligent, but also very effective mechanism in order to handle all of these requirements, right? And typically the memory management is something that is handled by the operating system, all right? So we are usually assuming that the operating system is the one that's handling all of these things. So of course, the first thing is that how do we share memory between multiple programs, right? The simple thing that we can do is that we can partition the memory statically and say that, okay, let's say, for example, let's say this first part is reserved. Then I'm going to just say that, okay, I'm going to divide the rest to the half. I'm going to give 1/2 to program A and 1/2 to the program B, right? and we're gonna be done with it, right? We happily then inside this, we're gonna like, oops. Inside this, we're gonna like maybe saying that, okay, this is the data section, this is the code section, this part is heap, this part is stack, this two grows this way and this way, and then the rest of it is like, environmental variables and so on, right? Statically, we are partitioning the systems and be done with it. The obvious, so two things that we need to, consider before actually seeing that what are the challenges with this. The first one is that, as I said before, we need protection. So we should make sure that, program one should not be able to change things in program two, right? So that's the obvious things that we need to do. And the same thing for program two to program one. And also another thing that we need to do is like location independence, right? Why? Because, for example, let's say we want to access array, like let's say A1, A2, A3 in one program, in program two. If you think about this, is basically just some location in the memory plus some values, right? So addressing some part of the memory with this. So if I, for example, put the beginning of program two at this point, this address would be something. And then if I like, let's say, swap these two and put program two here, then the address would be something else, right? But what we want to do is that we want to make sure that our programs run correctly no matter where we put in the memory, right? So our addresses should not be absolute addresses, but it also has to be within some offset, like where the program begins, and then all the addresses should be offset to that beginning. In that case, if we move that beginning to somewhere else, everything still will work properly because nothing changed in terms of the program's view, right? Any questions here? Okay, so these two things we want to know, and then for now, let's assume that you're just statically partition the memory into two pieces. And for now, just assume that we only have two programs, right? So how do we get these two things that I just mentioned? The first one is by checking some bounds, right? So what we're gonna say is that, okay, let's say this is the structure, this is the way that we're gonna partition this memory. So in that case, program one only allows to access memories within this region, right? Within this range. If program one tries to access something that is here, that is outside this range, we're gonna like block that request, right? We're gonna have like something like segmentation fault, knowing that the operating system is trusted. So if any program tries to access something that is not part, belongs to that program, the operating system can quickly detect that and blocks, right? So that's the first thing that we're gonna do. And the second thing, in order to have this location independence, as I already told you, instead of using absolute addresses, we're gonna always have the address as some base pointer, which is point to the beginning of some section, and some offset. So if we change that section to somewhere else, everything also correctly will be moved with it. Right. So that's the simple idea in order to make sure that we have location independence as well. This would be how as the hardware, that's how it would look like. So generally, the address that's coming from the CPU will be added with some base register, which this base register is that pointer that I talked to you, right? So it would be basically here, for example, for program one, or it would be here for program two. And then we can have multiple of these base registers depending on how many sections we have. Yeah.
I was wondering if in this case we would have any shared memory between the two programs.
We can have shared memory between the programs as well, right? Because essentially, when we are doing that bound checking, we can also add that range to the bound checking as well. So we need to do two comparisons. One is like, within that bound that we have, and also if the access is from the other bound that we are also sharing between the two.
But wouldn't there be a case where two independent programs try to sort of access maybe the same portion of memory?
They will, yeah.
Is that not an issue?
It's not an issue. It would be, so depends on like how many access you can handle at the same time. So usually if you have like a multi-core, so I mean, if it's a single core system, then what will happen is that we kind of like multiplex between the processes. So we run one process, and if that process wants to read something from the memory, we handle that. And then after some point, we context switch and run the other process. If you have a multi-core system, which is generally the standard these days, then it depends on how many ports and how many registers we have for the memory that can handle this. We can handle both of them. There are things called the consistency issues. So for example, let's say two program wants to write to a specific variable. So let's say we don't want to calculate the sum. We say core number one, just do partial sum, and core number two, do the partial sum. So there's the whole bunch of consistency issue that comes here, and there are a whole bunch of techniques that handle this. But that's like a computer architecture course about this. So for now, we just don't worry about that. Any other questions? Okay. So yeah, so just back into what we said, we want to make sure that each program cannot access the other program. So that's where we do this bound checking, right? So the address has to be within some bounds. So this could be like within some range, or could be multiple of this checks. And for that, you usually have like some registers that has those legal bounds, those valid bounds. And then for the address, we get this base plus the offset, right? And then if you see the terminology, we usually use this as the address or the CPU address. And the actual address that goes into the main memory to the physical memory is usually what's called physical address, right? So it's the one that's actually accessing literally the line in the memory that we want to read. And in this simple case, the physical address is nothing but the address that is coming from the CPU plus the address that is added by that base registers. And as I said, we can have multiple of these registers depending on how many partitions that we have in our system. All right. So simple as this. And this is the notion of address translation in some sense, because what we are doing is basically saying that the addresses that we have in the CPU is not exactly the addresses that we have in the main memory. So we need some notion of translation between these two addresses. In the simple case that I gave you, the translation is just nothing but this CPU address, which we usually say it's logical address, and we add that to some base, to some pointer, and there we're going to get our physical address or PA, physical address in that case. All right. And then when we are switching, for example, from program 1 to program B, all we need to do is basically substituting this base register to the base register that is relevant to program 2, right? So if you have multiple programs, all we need to do is just changing these base registers. Everything else will work normally and perfectly well. Any questions up to this point? Okay. And then back to your question, this is the way that we're going to share things. For example, we either share some part of the memory in order to read and write things, but more importantly, we need lots of libraries, right? So it's, for example, things like libc, printf, scanf, those kind of libraries that most of these programs going to use. One option is that we're going to replicate and create a copy of every single one of them in each program, which obviously not a great solution. What we can do is that we're going to have part of the memory for those libraries, and everybody has access to those. And what we're going to do is that, given that they're going to use this as utilities, we're going to make these parts read only, right? So for example, you don't need to change the code in printf, right? All you need to do is being able to access that part, right? So what we're going to do is that we're going to also add the notion of writing and reading in order to give access. So some part of the memory can be only read-only, which means that every process can just freely read that part. But if they're trying to write to that part, the operating system will block it. And some part of the memory could be read and write. So you're allowed to both read and write. And some part of the memory you may not be allowed even to read, right? So for example, for program 1, you may not be allowed to read anything for program 2. But for example, for the library, you're allowed to read, but you're not allowed to write. And for this part, you are allowed to both read and write, right? So that's the idea. And then, as I said before, the operating system itself is also part of this memory. So we usually reserve some part of the memory for the operating system itself, right? So this is like typically how our main memory would look like. But then the question becomes, okay, what will happen if the new program comes in, right? Given that we have a statically kind of like, partition our memory, what should we do if we have like a program 3, right? And the idea here is that, obviously we cannot easily do that. And then on top of that, like what will happen if we have a new program? Another issue that we might have is that what if program 1, for example, needs more memory than program 2, right? So for example, there are lots of local variables in program 1, but program 2 is just this tiny program, right? So this is also another issue that we are facing with this static nature of partitioning. So obviously, what would be the option 2? The option 2 would be, okay, let's do this dynamically, right? So static obviously has big issues. So let's go and dynamically partition the memory and make it kind of like demand-based, right? So if one program needs more memory, give the more memory to that program. And if one program don't need more memory, just start with some smaller predefined size. And this way we can kind of handle as much as many programs that we want, because we kind of like start with some small and then the rest of it would be equally distributed between all these different programs. So that's the idea. And how do we do that? So the very first thing that we need to do is basically we need to divide the memory into a smaller partition, which we usually call pages, right? So we're going to say that these are our basic blocks. These are our atoms in some sense in our memory. So what we're going to do is that we're going to say, okay, the smallest that we can assign to one program is 1 page, all right? So what is the size of the page? Depends on the architecture. In most architectures, usually either 2 kilobytes or 4 kilobytes of memory. So continuous 4 kilobytes of memory, that would be 1 page, and we assign 1 page to that. And then let's say, for example, if we have 3 different programs, A, B, and C, let's say for the beginning, we are assigning 4 different pages to each of them, right? So we say page number 0, 1, 2, 3, and same for program B and same for program C, right? So this way we can kind of like, share this between them. So as I said, usually each program, each page is 4 kilobytes. That's usually the standard, especially for Intel machines. And in a way that to actually detect, what is inside each page, the address can be divided into, the address can be divided into 2 parts. Since each page has, 4 kilobytes of data, usually we want to have our memory byte addressable. So we want to be able to address every single byte in our memory. In order to achieve that, we basically need to assign 12 bits for each page. So we have 4 kilobytes. We want to assign each single bytes in that 4 kilobytes. So we need 12 bits in order to be able to assign that, right? So we usually, reserve the first 12 bits in order to access the individual bytes within each page, and rest of it is just basically to distinguish which page it is, right? So let's say, for example, our address is 12 or 32 bits. The first 12 bits would be our bytes within each page. The rest of it would be basically the number of pages that we can in a given memory, right? Any questions here? Cool. And then, so this way, this would be our main memory, the updated view of the main memory. The interesting thing is that we don't necessarily need to put all the pages within, next to each other, right? So we can scatter, for example, pages for program A to anywhere we want in the main memory. And the reason for that is that we want to be able to dynamically assign this, right? So even if we start with, for example, something like this, if this one wants to grow, it has to go somewhere else in the memory, right? So we need a mechanism in order to scatter these pages into our main memory. And not only that, we should be able to recover them if we want to, right? So this would be the idea that we have here, that we basically create these basic blocks of pages, and then we put it in our main memory just And then same story goes for example, the operating system as well. The operating system also can be a collection of pages, right? Any questions here? And just repeating what I just said. So now the problem becomes, okay, how do we track which page is where, right? Let's say, for example, we want to address some bits within page number 1 of this program, given that each page can be potentially anywhere in our main memory. The idea of like having the base register plus the address no longer works, right? Because program, page 1 could be here, could be here, could be here, could be anywhere, right? So we need some sort of like more intelligence translation. We still need the translation, but the translation we have here is slightly more complex, all right? The idea for the translation is basically having some sort of mapping table, all right? So what we do is we are basically saying that, okay, wherever we're gonna, store this page, we're gonna have a table that what it does is basically just saying that page number 1 is map, of course, the beginning of the page, right? The beginning of this page number 0 is saved at this address P0. The beginning of page number 1 is saved at P1 and so on and so forth. So essentially think about a table that for each page we have one entry. And inside that entry, what we're doing is saying that, okay, where is the beginning of that page, right? And if we can do that, then we can easily, anytime we want to access something within this page, the first thing we need to do is that going to this table and see where is the beginning. That would be P1. And then all we need to do is that add the address that we have to the P1, and that would be our address that we are looking for. All right. So kind of like the idea of the base register that we have, but since we have many base registers, we're going to store them in some sort of a table, and we call that page table. All right. Any questions here? Cool. So we call this table page table. And obviously, we're going to have a page table for every single program that we have. So we have multiple page tables for any program that we have, right? And then the number of entries depends on how many pages that we're going to have in each of these programs, right? So this capability gives us this notion of what we call virtual addresses. The notion of virtual addresses means that we no longer need to deal with the physical address. For each single application that we have, what we can do is that we can start from like 0 and then assign the addresses each way we want. And then we're going to have this page table here that whatever address that we have here, we're going to have some sort of mapping here to the physical board, right? So it's a physical memory. So basically, if we could have like multiple 0 address, like this is 0, this is 0, could be many different addresses that are actually literally 0, but their mapping to the actual, physical memory could be different because each of them has a different page table. They're different mapping, so we are actually pointing to a different point in the memory, right? So that's where we come up with the notion of virtual memories, where each process thinks that they have the entire memory for itself. It has addresses, can use addresses from 0 all the way to whatever that maximum number could be. And then all we need to do is kind of like having a separate page table for each of these programs and to do the translation to properly address the memory that we want, right? So that's the idea of the virtual address. As I said, this would be the virtual addresses. This address is in our page table. The virtual address goes into this page table to get the physical address. And now we are ready to actually access the main memory, right? So this is the virtual to physical address translation that we're going to have. So this would be basically the life cycle of an address. We have a program. All addresses in our program would be virtual addresses. We have an address translation strategy that's translate these virtual addresses to physical addresses. And then we're going to go to the physical memory, to our main memory, bring that data, send it back to our program, and then continue So for every single access, for every single read and write, that would be the process that we're going to do, right? So why would we want virtual pages and virtual memory? The idea is that we want to give this illusion that every program has this private and unique and unified memory address space, right? So as I said before, for every program, we are assuming that we have, code section, data section, heap, stack, some reserve space, and so on and so forth. And we never say that, okay, these addresses are occupied for another program. We always say that you basically can start from address 0 all the way to the maximum. So let's say, for example, we have 32 bits addressing mode. We are saying that, okay, you can basically, for every program that you're writing, you can access anything from 0 all the way to the 2 power of 31 minus 1, right? And this way makes the programming much more easier. The programmer does not need to deal with, which address is where and so on and so forth. All of those will be handled by the address translation, all right? So that's the beauty of having virtual addresses and handling all of those things for the translation. Obviously, one big question that people usually confuse is that if every program has the entire memory for itself, and if we have multiple programs, how do we actually manage to put all of these into the actual physical memory? And more importantly, usually the actual physical memory might actually be smaller than, for example, to the power of 32, right? So for example, let's say you have 1 megabyte of main memory of DRAM. In that case, you have 2 to the power of 30, whereas you are assuming that your addresses are 32 bits. You have 2 to the power of 32 items in the memory. So how do we actually solve this kind of conflict? The solution to the answer to this is that while we do have access to the entire memory, to the entire virtual address, in reality, what each program actually use, it's much smaller than that 2 to the power of 32. So for example, although we are saying that the code section is this big, in reality, the amount of actual data that is stored in each program is just very tiny portion of that. Or another thing is that especially for heap and stack, we are giving this entire part for growing the heap and stack, but in reality, only, for example, 10% or 20% of that full amount is actually being utilized. Right? So if you add these together, you will see that it's actually way below that the entire capacity of the physical memory. Although you have multiple programs, each one might have potentially 2 to the power of 32, but in reality, none of them actually use even half of them. And given that they're not using the whole of most of it, you can actually just put them all together and store it in your physical memory. Of course, there could be a scenario where your memory becomes full. And that's where you're going to have things like segmentation faults and so on. There is usually the backup disk for this, which we're not going to talk about. So you have your RAM and you have your disk. And there is a mechanism for, if this becomes full, there's a mechanism. There's a mechanism for kind of like swapping the information here and here, which we're not going to talk about. But this way, we kind of also handle much more memory that we want. And this usually in order of terabytes. So it's much bigger than every individual program. So technically the combination of disk and DRAM would be much bigger than what we really want. All right, so this way we're going to handle this problem. Any questions? All right. So this is kind of like, the process of translating virtual address to physical address. Usually what we have is an n bits virtual address. So for example, the n bits could be 32 bits. As I said before, the first part of the virtual address would be what's called a page offset. And that is usually that 2 to the power of 12 bits that I told you. That since we want to have the page quite addressable, we need to have actually 12 bits for example, if you have a 4 kilobytes page, we need 12 bits in order to be able to address those. So we usually get rid of, we reserve that part for this. The rest of it is what's called the virtual page, right? And this actually goes into that address translation, that table that I showed you, in order to get what's called the physical page number. And the physical page number going to be added to this value here. So this value does not need to be translated. It's going to be directly added to this. And this will make our physical address that we want. So this is the actual address that goes into the main memory. All right. Here are some calculations if you're interested to know, how many bits we have for physical and virtual address. It's not important for this class that much, but if you want, you can take a look at that as well. So again, this is just a little bit more information of how this works. So as I said, the virtual page number or VPN goes to the physical page number table or page table. There we actually have this value here. So the content is actually goes here. And this way we're going to create our physical address. And then this table is basically there is one entry for everything, right? So this is a really large table. Depending on how many entries we have here, we're going to have one line for each of those in our physical page table. And then we're going to have for each program, for each process, we're going to have a separate page table as well, right? So this way we're going to make sure that no addresses, all the addresses have the translation that we want. And then one more important thing is that, within this address translation, it's not just the physical address that we store. We typically store some what's called flags. And those flags are, for example, to enforce that. Remember I said that some part of the memory would be read-only. That's where we're going to store this information. So when we have the virtual address, when we go to the page table to do the translation and get, we go to the page table to do the translation. That's actually where we also do all these checks. So for example, this physical address that we want to access, does this process really have access to that specific, is authorized to access to that page? Is this, address is write only or read only or something else, right? So all those flags are also stored within that page table. And then that's where the operating system will know that whether this access is authorized access or whether it has to be blocked and so on and so forth, right? So that's where we actually, all these things about accessing program 1 to program B and then not being able to write things and all those things will be enforced by the operating system. But that's where the isolation will happen, all right? So that's the main part of the security really is coming from. There are many challenges with the page tables, including where to store them, how to access them, and so on and so forth. For this class, it's not relevant. So far what we know about the page tables and address translation is all you really need to know. All right. So, if you're interested to know more, again, computer architecture courses where you're going to learn more about these things. So now let's go back to our buffer overflow attacks. This is enough for the background that we wanted to have. So again, now we know that how this actually created. For each process, we have this illusion that we have an entire memory for ourselves. The memory is actually dividing into the sections or pieces, the text, the data, and so on and so forth. The one that we are really curious about is this part that has kind of growing and shrinking depending on the access that we want. Part of it is what's called heap, and part of it is called stack, and they usually grow in the opposite direction. So if the higher memory addresses is stack, the stack grows into a lower addresses, and then the heap actually grows in higher accesses. And at some point, they will obviously get close to each other, but that's where the stack gets full, and there are some other things that we really don't want to talk about for now. All right. So now we know that. Let's see actually how the buffer overflow attack works. Let's have a very quick break here, and then we're going to talk more about this afterwards. All right, So far we understand how the virtual addresses works. In order to understand how buffer overflow works, you need one more piece of background, and that's what's called calling convention. So calling convention is basically a set of rules and mechanism in order to, when we want to call a function, what should we do in our stack and in our memory, right? And if you think about the function, basically when we are doing function, what happens, right? So when we are calling a function, so let's say we are in function A and we start executing things, and at some point we usually get this call, instruction, depending on which I say we are talking about. It could be a different instruction, but generally it's kind of something like call. And this call is basically transferring the execution of instruction from one function to another function. Let's call it function B, right? So we are basically saying that, okay, execute this instruction one by one. So this is the assumption that we are executing things in program order. We do it one by one. When we reach to this point, instead of like continuing executing these instructions, we are jumping to the beginning of this function, wherever this is. You can think about this as some other points in our memory. So we are jumping there and start executing that, right? And how do we actually keep track of where we are executing instructions? That's usually done by this register, this specialized register called program counter or PC. So starting a program, we start the PC from the beginning of that program, wherever that address is. And then we just usually add PC by one, increment PC one by one, execute next instruction, PC plus one, go to the next instruction, until we reach to some sort of a branch or a call, where instead of like, we are at this point, and instead of executing this call has this authority to change the program counter to some other value than PC plus one. So in that case, usually the PC gets PC plus some destination or target address, right? So that's where we're going to jump to. It could be negative or it could be positive. It could be somewhere upper in the memory or it could be somewhere lower in the memory, right? But the key thing is that the PC will change other than being just plus one, plus one, plus one. It would be PC plus some target value. And that target value would be the beginning of the other function. So that's the first thing that happens. We need to change the PC. The second important thing that needs to be happen is that usually functions need some inputs, right? So how do we actually pass that inputs to the next function? Two things we can do, right? So most of the processors has some bunch of general purpose registers, right? So depending on which ISA we are looking at, it could be EBX, EBR, and things like that. In Intel processors, if you're looking at things like ARM or RISC-V, usually it's called R0, R1, R2, R3, and so on. So these are general purpose processors. These are like, think about it as variables that you have access and you can play with. One thing that you could do is that if you, for example, want to pass, let's say this function gets two variable x1, x and y. What we can do is that, let's say R0 and R1 are those two registers that we can pass value on. So what we do is that whatever value at that point x has and whatever value that y has, we're going to put it onto register R1 and R2. All right. But if the function has 10 different inputs, what we should do is that we obviously have only limited amount of registers. So what we do usually is that, depending again on the ISA or the operating system, we have predefined and preset number of registers, usually 3 or 4, that we can pass inputs to them. If we have more than 4 inputs or 5 inputs, we're going to put all those inputs inside our stack. So basically, stack is this part of the memory that is shared between functions within one process. We're going to put all, let's say there are four additional inputs that we need to put. We're going to put it on top of the stack, right? And stack is shared between all the functions within one process, right? So everybody has access to the same stack. They exactly know where the beginning of the stack is, where the end of the stack is, and so on and so forth, right? So this way we can, safely pass any number of inputs to any function that we want. So that's number 2. And number 3 is the return, right? So when we, at some point, we reach to the return, and what the return does is that we always have this notion that if somebody calls a function, when we do return, we have to go back exactly at the place that we call it, right? So if you call this function B at this point, reaching to the return function of function 2 should transfer the control back to exactly this instruction, just the instruction right after the call. We obviously don't go to the call itself because that means that repeatedly we call the call function over and over again. So we have to go one instruction just below the call, and that's what the return address has to be. And how do we know that where to return? We have to kind of like have a mechanism saving that information when we're calling that function. So we're going to also put that in the stack as well. So we're going to have put some local variables, the inputs here. Usually after that, we put the return address right after it. And then we're going to jump here. When we reach to this return address, we're going to go and see where that address is stored. We're going to recover that. We do that PC plus that address, and that would be the address that we're going to jump back to. All right. So that's usually what happens with the call. Any questions at this point? All right. So it's kind of like, I mentioned all of these things. Another thing that we need to also be careful and do that is kind of like preserve the functionality of the stack. So what is stack? Stack is nothing but the actual memory and some point of pointers, right? So we usually call stack frame. Like for each function, we have stack frame, which is kind of like saying that this is the beginning and this is the end of those relevant stuff for that part of the function, right? So we usually have like, base pointer, BP or SBP, or depending again. And then we usually have like, stack pointer or SP. It's just showing that where is the top of this stack, because stack is something that, it's a FIFO, first in, first out, right? Sorry, last in, it's a last in, first out kind of thing. So if you push something to a stack, if you pop it, that would be the first thing that you're going to pop it. So we need to know exactly where the top of the stack is. And you also need to know what is the beginning of that for that function where the beginning of that stack is, right? We usually call that the frame pointer or the base pointer, and this a stack pointer is usually where it points to the top of the stack. So if you push something to the stack, depending on whether the stack grows upwards or downwards, this has to go upwards or downwards. So for example, let's assume that it goes this way. If we push something else to the stack gets bigger. And what we're going to do is that we're going to now point to this point of that would be our new stack pointer, right? The frame pointer doesn't change. But when we are jumping from one function to another function, we need to update this frame pointer, right? So we need to say that, okay, these are the things that are relevant to function A. Now that we are jumping to function B, we need to update this base pointer to here, basically, because everything from now on would be this way downwards, right? So we're going to also update our base pointer. And not only that, we also need to remember and store where was the previous base pointer, right? So we usually, when we are putting our local, inputs, the return address, we also put our frame pointer or base frame pointer here, all right? BP here. This is for the function A, right? So we also put that here. And this would be our stack, basically. And then we're going to say that this is the beginning of our newer stack, right? So this would be our the new base for our stack for function B. And then once we return, we need to, again, recover this and then do the base pointer back to here. All right, so this way is not like nothing happens ever, right? So we always recover where the base was, and then we just continue function A correct, right? So this way we kind of like, no matter how many times you call different functions, you can have nested functions and so on and so forth. You recover the previous stack pointer, go to the next one, do all those things. You return back, you recover the base pointer, and then return multiple times until you reach to the, the top of this chain of call, all right? This is the way that we ensure that no matter how we call this, we always manage to correctly execute things and nothing happens. Is that clear? Any questions? Any questions in Zoom? Cool. So I already show you how this works. So let me just give you one more time to look for the stack. As I said, the stack is basically part of the memory. It's not something specific. It starts from some address and ends in some address, but it can grow as well. So usually the stacks would be the inputs. So usually, let's say A0, A1, A2, depending on how many inputs we have. After that, we usually have the return address, right? The RA or return address. We will have the previous base pointer, right? So we have the save base pointer, and we're gonna have a bunch of different local variables within that function. So because the stack is also used for temporary saving things, right? So that could be, for example, if you want to, like, let's say, do A plus B equal to C and then use C later. Typically what we do is that we push C into the stack. So that way would be much more faster, right? So it's for storing local variables in your functions. We usually use stack as well. So this way, this would be the area for storing those things. And depending on how many local variables we have, this can grow more and more, right? And then, as I said, we always have the new base pointer is basically gonna, point to the top of this function. And then also the stack pointer is always showing the latest things that has been added to the stack, right? So for example, in this case, the stack pointer would be somewhere here. All right, so this would be how our stack would look like after calling a function. Any questions? Cool. So now let's actually start thinking about the adversary and how we can exploit this. And the first question is, actually, can we overwrite the stack? And we're going to show you how to do it and how this could be useful for attack purposes. So the very first thing is that how do we do it, right? And the answer to that, unfortunately, is very simple. And that's the basis of the buffer overflow. That's the cleverness of the buffer overflow. And let me give you an example. So let's say we have a function called foo that gets some inputs, int a or something. And this foo has, a bunch of different activities. And at some point, it's kind of like had some, like, let's say a function like get name, and then doing something else. And then let's say this name is actually something that we are getting from the standard inputs from the terminal. So let's say that, for example, our stack, going back to what we showed before, those inputs, frame pointer, return address here, and then a starting bunch of local variables. The way that we usually define this is that we are saying that, that, for example, this name is a char, and we're expecting that this char would be, for example, 2 bytes, right? And as I said, that since this is byte addressable, whenever we define this name character, we're gonna, reserve 2 lines in the memory, and we're gonna call this name, all right? So this would be our name variable, right? So as soon as you define this, the compiler will push the stack 2 position down and then give you a space for name. And the expectation is that when we are calling this function, we're going to get 2 bytes of value and put that into our name, right? And then move forward. And most of the time this happens, but a clever attack can do this, that if we don't check how much value we are actually writing to name, what we can do is that instead of 2 bytes, why don't we write 4 bytes? Why don't we write 8 bytes and so on? And now look what happens if we do more than 2 bytes. Since the stack is kind of like growing, written in this way, if I write 2 more bytes, I will overwrite this and this as well. And the interesting thing happens when I, for example, do 5 bytes, where I also overwrite this, right? So basically what I can do is that when the gets, for example, name function is called, and it's actually getting inputs from the, for example, standard inputs from some information remotely, the attacker, instead of sending a regular word that is 2 bytes and you're expecting, it can send a really, really long string, which actually happens to be more than 2 bytes or 4 bytes or whatever we are expecting. And this way, not only that 2 bytes that is predefined for that specific variable will be overwritten, but everything above it would be also overwritten. And if there is no check that is actually checking how much we are writing, technically we can write all the way to the top of the stack. So we can write everything that we want all the way, right? So it's that easy that we can actually overwrite the stack. And this is what's called the buffer overflow attack. So I'm showing like the picture one more time here. So remember, as I said, each program sees the memory this way. There will be some heap, some data, some text, some stack, right? And within the stacks, we will have the function, parameters, return address, base pointer, and then local variables. So let's say in this case, we have what is called a buffer, which is 20 bits, right? And instead of like writing 20 bits, what we're going to do is that we're going to write 30 bits or 40 bits, right? So what will happen is that not only this part would be overwritten, but this base pointer will be overwritten, and more importantly, this return address will be overwritten, right? So that's the basis of what is called stack overflow or buffer overflow. That we are overwriting things in the stack without the knowledge and without any by having complete control of the stack of the program. But and only thing that we do, not circumventing any security mechanism here. All we do is that instead of sending a correct expected inputs to the system, we are just sending something really, really long, right? So that's the basis of very simple but extremely dangerous attacks for memory systems. Any questions here? Cool. So let's take this one step further, and instead of saying, okay, we want to just, this is more of like, we are just trying to kind of like break the system, right? But we can actually be much more, as an adversary, we can be much more smart than that and use this to do even more dangerous attacks. The main thing that we can do is that, as I kind of like emphasized multiple times so far, is that the buffer overflow can overwrite things, including the return address, right? So what we can do is that when we are doing this seemingly random overwriting, instead of randomly overwriting things, we can actually calculate when we reach to the return address, and the value that we're going to overwrite to the return address would be actually a valid value. What do I mean by valid value? It means that the actual address somewhere else in the memory. So for example, let's say I for some reason wants to jump to this address 0x100, and then we want to overwrite 30 bits. I know that the first 20 bits is the actual buffer, and the rest of the 10 bits is actually, part of it would be, for example, the frame buffer, and part of it would be the return address. And by knowing the details of the system that I'm dealing with, for example, I know that the first 4 bits is for the frame buffer, and the rest 6 bits or something would be the return address. So what I'm going to do is that I'm going to start with 20 bits of chunks, right? So 0, 0, or whatever. Then 4 bits of, again, chunks. But then its next 6 bits is the actual return address that I'm going to overwrite, right? So after this process, what will happen is, it's what's called, stack smashing attacks, or buffer, or still some people call it buffer overflow attacks, where essentially if the original, stack looks like something like the array, the frame pointer, and some local variables, after I manage to attack the system, I get some chunks here, some chunks for the frame pointer, but I get the address that I want, right? I get some address that I pre-planned it. And what will happen is that when this function, this function foo, executing things and gets to this get name, it has no idea that things in the stack has been overwritten, right? So it just normally execute the rest of the instructions. When it actually gets to return address, what they expect is that if it goes to this point here, it's going to read this return address and it's going to jump back to the function that is called from, right? But since we have overwritten this, it's without this knowledge, it's completely innocently and without the knowledge of like this actually being overwritten, instead of jumping to this return address, it's actually jumping to this address that we have planted into the memory. And instead of jumping to the function A or whatever that original function was, we're jumping to the where the adversary wants it, right? And now think about that the adversary can kind of plant any arbitrary function somewhere into the memory. That would be a separate attack, obviously. But for now, let's assume that the attacker managed to store some malicious program somewhere else in the memory. So we have this memory. As I said before, we have a bunch of different programs into the memory. And for now, let's assume that this part of the memory is actually where the malicious program has been stored. And for now, we are executing this part of the memory. By this return address, we are basically at some point, we're going to force this program to jump to that part of the memory. And this is what's called control flow hijacking. So we are hijacking the execution of the instructions. And instead of actually jumping back to the function that we are expecting, we are forcing and hijacking this control flow and jumping somewhere else in our program. And how this could be helpful? For example, let's say that this is your password checking. And for example, you're calling your password checking and just type random password. And you're expecting that normal program would be the one that reject this password and like create an error. But instead of jumping back and print error, we are jumping to somewhere else in the program that is actually it's as if that the message has been successful. So like we're gonna get an unauthorized logging access to our system, right? So we are expecting to write turn in the right password. We are instead we are just turning a really large and really long string, which caused the buffer overflow. And although that this has to be rejected, since we are hijacking the control flow, it's actually jumping to somewhere else in the program, which is kind of saying that, okay, this password was correct. And then we're going to continue correctly executing this. So it's kind of like stealing the password of the system with this seemingly simple attack. All right. Any questions? Awesome. So that's what's called the buffer overflow attack. And this part is kind of like usually called stack smashing or control flow hijack, right? So just to give you like a step-by-step. So we need to find first the buffer overflow vulnerability. What is the buffer overflow vulnerability? There are things like this get s that doesn't check the bounds. So this vulnerability is when we are reading something from the input domain without actually checking the bounds of that. If we had checked the bounds, we would have stopped these attacks, but more often than not, unfortunately, these bounds doesn't be checked, right? So that's what's called vulnerability. So first of all, we need a vulnerability like that. We need scenarios like that we are reading from the input domain without actually doing the check. If we have that, then we can, as the attacker, first find those vulnerabilities. The second thing is that we need to put our malicious code somewhere into the memory. So that's the part that once we hijack the control flow, we want to jump to that. We usually call that shell code. The reason for shell code is I'm going to explain a little bit later, but that piece of code is usually called shell code. Then we need to actually launch the actual attacks. When we're calling that function and putting that input, we need to create the input intelligently such that the return address would be overwritten, and the overwritten value would be the value that is pointing to the actual part of the memory that our shell code is resides. So this would be our memory. This would be the part that we put our shell code in. And we need to kind of like find this address and making sure that when we are overwriting the buffer, the return address is actually pointing to this. So some sort of reverse engineering is needed, but it's not that difficult to actually achieve that. And then the rest of it is going to be done automatically. That function will be called, that input will be given, the stack will be overwritten. We reach to the return function, and that's where the control will be handed to us as the adversary. Now we can execute our own program within that same program that we are expecting to be safe, right? And that's where the beginning of the malicious activity, right? So we can now do whatever we want within that shellcode. And the beauty of this is that you can basically run anything that you want as your shellcode, right? Nothing prevents you to do any sort of malicious activity that you want. All you need to kind of figure out the way to put this malicious code inside the same memory space as the victim. But if you manage to do that, and there are simple ways to do that, then you basically can run anything you want with that application, right? So that's the step-by-step approach for the buffer overflow attack and control flow hijack. Any questions? Okay. So now let's talk about how we can actually even improve this. So the first thing is, so I said that we need to jump to somewhere else in the program, and that's where our shellcode will be staying. But what we can do is that we don't need to actually pre-inject that part of the code, given that we are basically overwriting everything into the stack. One thing that we can do is also, after the return address, we can also put our own code that we want to run. So not only we overwrite the stack, we also add the code that we want to run in the rest of the stack. And then when we want to return, we just point to the beginning of that piece of code. So we have our shell code, and we have our return address. We managed to overwrite this. And then what we can do is that we can continue overwriting, but this time with the actual program of the shellcode. So the values that we're going to overwrite from after that point that we overwritten the return address would be the actual code that we want to execute, right? So we write that program, we get the values, the zeros and ones, we change them to strings, and then we also overwrite that when we are overwriting the buffer overflow. And the next thing that we need to do is that just computing how long that program will be, how many bytes it will occupy in our memory, and then this return address has to point to the beginning of that. So when we are jumping, we're not only jumping to that part, we also inject that part as part of the buffer overflow. And this is much more powerful than what I just described, because then essentially that process of putting my own malicious code somewhere into the memory is also kind of solved, right? Because we no longer need to have like a separate steps of putting my my malicious code somewhere into memory. As I do the buffer overflow, I also do that part with it, right? So this is also what is done usually. There are some challenges. For example, we don't know exactly how long that program will be and so on. So in order to make sure that this actually works correctly, we usually add some no-ops before the program as well, in order to which we usually call it the landing area. So our program, so let's say our program has this many lines. What we will do, we add some no-ops, no operations, which no-ops are just instructions that if you execute, nothing happens. So you just keep executing them one by one. What we do is that we add some no-ops on top, and then the return address this way, the beauty, I mean, the benefit of this would be that we don't necessarily need to find this exact address. Anything in this range will work, right? So if we put it here, here, or here, all of them will result in a successful attack. Why? Because if we start at this point, we will execute some no-ops and then start our program. That works. If we start at this point, we first execute more no-ops, but then eventually start our program. So basically, we are kind of like, increasing our landing area, so we don't have to exactly find where the beginning that address should be. Anything in that range will work. And the reason for that is that there are challenges to finding that exact address, but this way the chances of finding that beginning is much more high. Because even if you are off by a few bytes here and there, you always start executing some more or less no-op instruction first, and after that our program will start anyway. All right, so that's what the attackers usually do. All right, so that's kind of like again, summary of how the buffer overflow works. This is the buffer, this is the base pointer, this is the original return address. What we're gonna do is that we're gonna override all of these with these things here, and then the address that's going to replace this would be this buffer address that points somewhere into this landing area, and anywhere that you execute this is fine. What it's going to do is that it's going to execute these instructions here, which all there are no ops, and eventually going to reach to this point, which is the beginning of our shell code. That's malicious code that we have, and going to start executing this one by one, and then we're going to then have the full control of the system. And the reason that we call this shell is because the best things as attacker can do is spawning a shell, right? So two options that you have, right? So as the attacker, you can either, let's say you have a specific agenda, you have a specific target that you want to achieve. So you write a specific program and put that in your shell code. What is more important and more interesting is that if you can open an actual shell, open an actual terminal, after that, you can actually run anything within that terminal, right? So you're not limited by one application or another application. Once you open that terminal, then you can run any application, sure, right? So that's why we usually, instead of actually running a specific program, we run a shell, opens a shell, and that would be our malicious program. So once you open a shell, we have a shell within one program. Now we can run anything that we want. So remotely, I'll do that, and I'll see that a shell pops up remotely for my remote connection, and then now I can start anything that I want with the root level accesses. That's the main things that the attacker wants to achieve. All right. Any questions here? Okay. So of course, how common is this? As I said, this is a very, very common thing. And the reason is that there are many buffer overflow vulnerabilities exist even today, because there are many unsafe, functions and bugs. And usually this comes out that not because of the negligence, but because of the bugs that you run. So you forget to check some bounds. The software becomes too complex to do that. So you can find these buffer overflow vulnerabilities in many of these systems, all right? So that's why still, although years and years pass by, there exists this type of vulnerabilities in systems, all right? This actually, if you look at this table, this is the most dangerous software weaknesses in 2020. And you can see that still the second most dangerous problem is what's called out of bound writes, which is basically this buffer overflow things that I just described. All right. So it's still one of the key issues, one of the major issues in computer security. All right. So now let's talk about how do we defend against this. So as I said, since this is like a very serious problem and it's been around for a long time, there are a series of different defense mechanisms for it. We're going to talk about a few of them, but just let me go quickly over different options. So the very first thing is what's called safe codes and languages. There are codes like Java, more recently things like Rust, that essentially automatically do these checks for you, right? Remember, we said that the reason that we have buffer overflow vulnerability is that because we are writing things and we don't check how long they are, so we just make an assumption. There are, programming languages that gives you this automatic checks. Unfortunately, C and C++ is not part of that. And since the majority of things that we write is based on C and C++. That's why we are having many, buffer overflow vulnerabilities. But there are new languages that are safe by design, which does this checks for you. All right, so that's one thing that you can do. The second thing that can be done is by the compiler. So the compiler can also put some additional checks and put additional instructions. So for example, can check whether like automatically add instructions to see if the size is bigger than what is expected, it rejects it, and so on and so forth. So at the compiler level, there are methods for protecting that. There are stack protection mechanisms which we're going to talk about, especially the major one is what's called stack canaries. That's kind of like solve this problem. We're going to talk about this in the next few slides. Another interesting thing that can happen that I'm going to also talk about is control flow integrity. Also, another thing is pointer authentication. So the pointer authentication is this fact that, what we can do is that whenever we want to jump to somewhere, we can always, see where the legal transfer are, and then we can kind of like, store a MAC. Same way that I said that, we can ensure the authenticity of the values using the message authenticity codes. Like for example, if you do the boot process, what we can do is that we can check whether those values are correct values. For return addresses, we can also extend this notion. So basically, whenever we want to return, we not only store the return address, but we also store the MAC of that return address with it. And in that case, if somebody tries to overwrite that return address, they have to also find the MAC for the new return address as well. And as we talked during the cryptography, lecture series, lecture session, we said that finding a MAC, finding an arbitrary MAC for an arbitrary, value is not possible unless you have the secret key. So if you don't have the secret key, you cannot create that. So you cannot just jump arbitrarily to any direction there. Right? So that would be another way of doing that. But of course, it has its own problems and challenges. Another two things that I'm going to talk in the next few slides is data execution protection and ASLR. Right? So I'm going to talk about those things as well. Let's first talk about stack canaries. So the idea of stack canary is very simple and very interesting. So what it does is that, remember I said that essentially our stack would be, some local variables, the frame pointer, and the return address, right? So what we can do is, and then what happens is that this buffer is actually kind of like overwrite everything, right? So what we can do instead is we can put a random variable or some secret variable called the canary. So this would be our local variables. This would be our canary, which the canary is the bird canary. This canary would be, let's say it's a random number, and this would be our frame pointer, and this would be our return address. So if what we can do at the end when we are returning to the original function, when we are reading this, when we reach the return address, what we need to do is that not only popping the return address from the stack, we also need to pop this return canary, this canary value, and check it with the correct canary value that we are expecting. If these two numbers are the same, the assumption is that the buffer has not been overwritten. If these two numbers are different, then it means that the buffer has been overwritten. And the idea is that the attacker does not have any idea what this canary value is, because it's something internally generated. It could be a secret value, or it could be a random value. So when you're doing the buffer overflow attack, you have no idea what this canary value is. You have to find a way of guessing it, but usually it's very difficult to do that. So if the buffer overflow happens, as I said before, it's going to start overwriting everything. And it's going to also overwrite this canary value as well. And when we are actually doing the return, we're going to pop this and check with the correct value that we are expecting. And since we have overwritten this, these two values would not agree, would not be equal to each other. And this way we can detect an attack that happens. All right, so this is like a very neat way of protecting the systems against buffer overflow attacks. Any questions? But of course, this is not the end of the story. What happens is that there are ways to get this canary, to find this canary, to save this canary somewhere else, and then overwrite, the stacks and so on. So the idea of, stack canaries has been around for about 10 years, but there are more modern attacks that kind of actually find a way to circumvent this as well, right? So it's not that, there is a perfect solution here. I don't think we have any papers that talk about this, but I mean, there are nice papers about attacks and defenses against the stack canaries. All right, any questions? Cool. Another possible protection is what's called data execution prevention, or DEP. So the idea of DEP is, well, I mean, you can have stack and you can store things from stack, but why don't you make your stack executable? So the reason that we can actually send instructions and inject instructions in stack and then do the buffer overflow is that we're assuming that in order to execute instructions, we can read instructions from the stack as well, right? But if we make the stack only read or write only and not executable, right? What will happen is that regardless of what the attacker does, so as I said before, the attacker overwrites this, overwrite the rest of the things, and it's going to inject his shell code here, right? And then the assumption is that, the attacker is going to jump somewhere here and then start executing the shell code, right? So what we are arguing is that what we can do is that we can make sure that this range of the stack is non-executable. What does it mean? It means that if the PC is ever within this range, we're going to block the execution of that. We're not going to allow the operating system to execute the instruction within this range. And this way, we're going to make sure that even if the attacker overwrite things and inject his own code to the stack, still will not be able to execute that because the stack is non-executable. You can write it, you can read it, but you cannot execute instructions. So we are basically adding the notion of executable to memory as well. So we said that things could be read only or write only or read or write, right? So another thing that we are adding is the being able to execute things. And then we're going to add this to that page table configuration that I described earlier in the lecture, that essentially we're going to, for every instructions that we're going to fetch and start executing, we're going to first check whether this is within the range that is allowed to be executable or not, right? So this depth or data execution prevention is very, very powerful defense against both buffer overflow attacks. Any questions?
Doesn't that actually harm the program state? Because even though you cannot execute it has already overwritten some of the stack, which might have full information.
Yeah, it still doesn't completely solve the problem of buffer overflow, but solve the problem of injection of your own code. So it significantly degrades the impact of the buffer overflow attack. Because then in that case, the attacker has to find another way to injecting his own code. And that's not an easy task. So it doesn't remove the challenge, but it makes it much more difficult. Okay. But I mean, soon I'm going to actually describe a method to even circumvent this. So wait for it. Another possibility is what's called address space layout randomization, or ASLR. So the idea is that, I told you that, each program has this very well-defined code section, data section, heap, stack, and so on and so forth. And this well-defined and expected behavior makes the life of attacker much more simpler, right? Because the attacker can know exactly where the frame pointer is, where the return address is, and so on and so forth. So the idea of the address space randomization is that either the operating system after each boot, or even sometimes in the middle, just move things around, right? So given that we are doing the address translation anyway, we can just move things around as much as we want. So this way, the attacker has much more harder job to detecting exactly where its code has been stored, like where the return address has to be and all those things, right? So if we continuously move things around, then the chances that the attacker can actually find where to, for example, jump to, where the buffer overflow actually is, how to, override the stacks, and all those things becomes much, much more difficult, right? So that's the idea of the ASLR, that we want to have randomization in the process. Doesn't impact the performance that much because still we do the translation anyway, but for the attacker perspective, that would be much, much more difficult, right? So that's another thing, is that that's another defense. And again, unfortunately, this can also be broken. And the idea of this is very neat, actually. So even though that you can move things around, if you can find one points, so basically, let's say you have different shapes, and I just randomly move these shapes around. If I just for some reason know that the relative positions of this, they're always the same relative position. As soon as you find, for example, partially that this is, for example, a circle, you can quickly recover the entire circle, and then you can quickly recover where the rectangle is and where the other shapes are, right? So the idea of this attacking the SLR is also the same. Attacker found one position that like what part of like a data section or code section is. They managed to find the entire data section, then they managed to find the entire code section, and then after that they kind of like slightly find all the other parts of the system as well, right? So the ASLR is helpful, but again, it could be it should be like there shouldn't be any sort of leakage about any point of the program, because otherwise the attacker can use that portion information to gradually and slowly find the other things and then piece them together in order to find the entire layout of the memory, all right? So actually, if you're interested, that's a very, very nice paper, the first paper that kind of shows that the ASLR can be broken as well. All right, any other questions here? Okay. And another thing that I say, another defense for these methods is what's called control flow integrity, or CFI. The idea of the CFI is we only allow changing and transferring the control if you already know that that control transfer is legal. So for example, let's say we call from function A, we have function A, and then we call function B. So this jump from function A to function B is a control of transfer, right? And then we start executing function B. And then at some points we want to return to this, to this point here, right? So this transfer of control can be only allowed if we know that we have seen this before, or is part of like some sort of like a whitelist, all right? So otherwise, if you're jumping to somewhere random that we haven't seen before, this seems malicious, so we can block it. So the idea of control flow integrity is that kind of having a list of expected targeted for each return address and making sure that we only allow those lists and block everything else. So this way, we kind of like the attacker cannot jump to any arbitrary location in the memory, because that location has to be kind of seen before. Otherwise, we're going to block. All right. So this is kind of like we're checking the integrity of our control flow, the flow of instructions that we have. Of course, there are two main challenges in CFI. First of all, we need to find a very effective way of finding all these legal transfer. And this is actually a quite challenging task. And the reason for that is that we have many different paths and many different branches in our program. So actually quantifying that is not an easy task at all. It's actually, we're going to have what's called a branch explosion problem, where we have many different branches, and within that branch is going to have other branches and other branches. So with the exponentially, the number of branches and number of paths going to grow, right? So we cannot really say that, oh, it's very easy, we're going to have all the legal transfers. Finding that is not an easy problem itself. And the second thing is enforcing that. So how are we gonna in runtime make sure that this transfer is legal and that transfer is not legal? You can know that by having that list, but how do we block that and how do we enforce that? That's a separate story that we need to find. But CFI is actually very hot area of research, been around for some time, getting some momentum again. I think one of the papers that we're going to discuss on Friday would be around this topic. So we're going to, well, let's people are going to describe this, talk more about the CFI itself. All right. And as I said, I mean, the story that I told you so far is always this, vulnerability fix, new vulnerability fix, new vulnerability fix, and so on. And I told you there are multiple different defense mechanisms, but unfortunately, all of them, there has been a new attacks that's kind of like, try to find a new way of circumventing this. One of the most newer version that's very, very powerful, even more powerful than buffer overflow, is what's called return-oriented programming, or ROP. The difference between ROP and the normal buffer overflow is that in what we do is, give me a second. So what we do is instead of like injecting the actual payload, so instead of jumping to that point into the program, we are basically reusing the existing code into our memory. So for example, the main one which we usually use is libc. Remember I said part of the memory are these libraries, right? So what we can do is, if we are hijacking the control flow of this program here, instead of jumping to somewhere malicious, we can jump to somewhere into the library with some specific input. Why this would be helpful? The main thing in this library, this libc library, which is mainly available in almost every standard programs, is that there are interesting functions here that could be very helpful. Remember I told you that we want to invoke a shell? Actually, invoking a shell is part of the standard functions in the libc. So what we can do is that we can actually jump there and start executing the shell and get the shell out of there. And there are some minor tweaks that we need to make that I'm not going to talk about. But instead of actually jumping and injecting our own code, or making sure that our own code is somewhere in the memory, libc is always there. So why don't we use that in order to attack the system? All right. So this is very clever, and unfortunately, there is not much we can do because this part has to be. Oops. This part has to be executable because we want to have libc. One option is completely removing libc, but that's not an option because we want things like printf and so on. So there's not an easy way to actually, defeat this attack, unfortunately. And even more interesting is creating the gadgets. All right. So what happens is we are creating a sequence of instructions that ends with a return. All right. So let's say we have add XOR something, and then actually it gets to the return. If you find lots of these gadgets, what we can do is that we can create this what's called a chain of this. So basically, what we do is that let's say we do add, XOR something and then return, and then we have another gadget that does, for example, compare, branch, and then return, something like that. So what we can do is that basically we can keep adding and running these instructions back to back. Always, all we need to make sure is that the return address of this pointing to the beginning of the next one. So we can create this long chain of instructions that all ends with the return, and the return is basically jumping to the next chain and next chain and next chain. And all we need to do is basically initialize it with the beginning of that chain. And this way, we can basically create an arbitrary instruction or just searching through the program memory and find these gadgets and then just chain them together. So this is actually also very clever attack. But all it needs to do is that going through the program memory, for example, look into the libc that exists in almost all program memories and find these gadgets that's kind of like list of instructions with the return. list of instructions with other returns and so on. Find the address of them. All you need to do is that do the buffer overflow with these addresses, point it to the beginning of that chain, and then start executing them. So you start executing instructions, you do return, go to the next gadget, and next gadget. And actually people have shown that this is very, very powerful, that you can create any arbitrary, instruction, as long as your libc is big enough, which it is, you can basically run any arbitrary program. So basically it's as if that you're writing your own program by just using these gadgets. All right. So the ROP is actually just like ultimate way of attacking the system by just finding these gadgets and then chaining them together. And then, for example, if you want to do add, XOR, subtract, something, you just find these gadgets and then just run them one by one. Right. So that's the story of return-oriented programming. I think there is one paper on Wednesday that we're going to talk a little bit about this. So we'll learn more about that. And then there are many other attacks as well, like integer overflow, use after free, format string vulnerabilities, and so on and so forth. If you're interested, take a look at these as well. But again, the major one is really buffer overflow, but there are many others as well. And this one is kind of like, a very nice paper that give you a summary of these different attacks. I suggest you take a look at this and see what are the differences. It's kind of like, step-by-step flow of the attacks, what will happen with each one and so on and so forth, right? So take a look at this to see what are the differences, which one is control flow, which one is data only, which one leads to information leakage and so on and so forth, right? And then the last thing that's kind of very quickly in 2 minutes I'm going to go through is what's called binary analysis or symbolic execution. So as I told you, the problem it actually happens because we have bugs, right? So one thing we can do is that, of course, we can do all these sort of, if there is a bug, make it more difficult for the attacker to exploit it and so on and so forth. But we can actually tackle the root cause, which is the actual bugs, and try to find them, right? And in order to find that, this actually, this is a large area in software engineering, which is, doing the binary analysis and symbolic execution. And the idea here is that, we want to investigate the code to find, for example, scenarios where we kind of potentially have buffer overflow vulnerabilities, right? Of course, we can do it statically. We can start, looking at some set of rules, defines that set of rules, and then tries to find them. And this is like an area in software testing. But what we want to do mainly is being able to do that dynamically. And the reason for that is that we have scalability issues with the static software, right? So that's where the idea of symbolic execution and dynamic binary analysis comes into play, where essentially we want to have some set of rules, for example, saying that whether we have an unbounded checks on unbounded writes, and find the inputs from the beginning of the program in order to find that path. All right, so let me give you a quick example. Let's say we have something like this. We have a bunch of if analysis. And then, for example, we want to see what would be the inputs that cause z equal to 2, right? So what we're going to do is that we're going to create this symbolic execution where instead of saying that, we have concrete values for A, B, and C, we're going to have symbolic values, alpha, beta, and alpha and beta. And then based off that, basically, we make the decision that whether this, Z is equal to 2 or not. So for example, if we look at this, if alpha is true, it means that X is equal to -2, right? If alpha is false, it means that X is not equal to -2. So we're going to go to the next one and next one. So if you actually follow both of these paths, you will see that, for example, for Z equal to 2, we have these 3 different conditions that reach to this condition here, that alpha and with beta less than 5 actually will lead to this scenario that Z is equal to 2, all right? So this way we can actually find the inputs find the condition on alpha and beta in order to actually find that v equals 2. And then if we solve this equation, we can actually find alpha A and B and find that inputs. We don't have much time to go over this more, but I'll probably just talk about it at the beginning of the next class. All right. So thanks, everybody. And see you on Wednesday.